The objective of this lecture is to provide a first part of the study of interplanetary orbit transfer. And as stated, this is part 1. So the study of interplanetary orbit transfer is going to start as follows. First, we're going to define an interplanetary orbit transfer. So an interplanetary orbit transfer is a transfer of a spacecraft from an orbit about one central body to an orbit about another central body. Now, generally speaking, these bodies are planets. So we can think of an interplanetary orbit transfer as a transfer from an orbit of a spacecraft from an orbit about one planet to an orbit about another planet. And in going between the planets, because we're actually going from one planet to another, there's going to be a segment where the spacecraft is going to be under the influence of the gravity of the sun. So as a result of transferring between these bodies, the spacecraft will also take a segment where it is under the influence of the gravitational field of the sun. So, as a result, an interplanetary orbit transfer has 3 phases. The first phase is a departure phase, or it's also called escape phase, from the first body. Then the second segment is a heliocentric phase where the spacecraft is under the influence primarily of the sun, and then a third phase, which is an arrival phase or capture by the second body. So when I talk about the first and second body, what I mean is we can think of these again as planets. So the first body is the planet, the second body is another planet, and then in between is the sun, which of course is also a body, but we're really thinking about the bodies, first and second bodies, as being planets. So the structure now requires that a discussion be be given of all three of these phases. But it turns out that the way to start this is by looking at the second part first, the second phase. So that's the starting point and where we're going to actually start this lecture. Now, it may not seem like that's the right place to start, but it actually is, because we need to understand what happens under the influence of the sun first before we get into the escape and the capture. So this lecture is going to focus on the heliocentric phase of the transfer. And the way we're going to do this is as follows, is that we are going to develop the following key results in this lecture. The first one is we're going to describe what's called an interplanetary Hohmann transfer. Now, we've looked at a Hohmann transfer about a planet before, but this is an interplanetary Hohmann transfer, which is actually going to be a transfer that's going to take us between two orbits relative to the sun, and we'll describe what those are in just a bit. The second part is going to be discussing what are called rendezvous opportunities, which are times when the it's possible to be able to start a Hohmann transfer. So rendezvous opportunities are times, or I can actually say it this way, configurations where it is possible to start an interplanetary Hohmann transfer. And we're going to discuss both of these in this lecture. So let's start with an interplanetary Hohmann transfer. So an interplanetary Hohmann transfer of a spacecraft is performed in the following manner, which is that suppose we have two planetary orbits. They're going to be coplanar circular orbits. So consider the orbits, the coplanar circular orbits of two planets. So this is really important here. These are coplanar circular orbits. Now, we're going to call the radii of these two planets R1 and R2. So R1 is the radius of the orbit of planet 1, and R2 is the radius of the orbit of planet 2. Now, what we're going to do is we're going to actually consider that the spacecraft is in one of these orbits, and we want to transfer it to the other orbit. So the spacecraft starts in the orbit of planet 1, and we want to transfer it to the orbit of planet 2. So the spacecraft starts in the orbit of planet 1, and it is desired to transfer the spacecraft to the orbit of planet 2. Now, this is what the picture actually looks like. So here are the two planets, the two orbits. This is the orbit of planet 1, and this is the orbit of planet 2. And it doesn't really matter which orbit is bigger, but we're just depicting it this way as the Sun is in the middle, and the first planet has a radius, the first orbit has a radius r1, and the second orbit has a radius r2. Now, the goal is to be able to transfer between these two orbits. So this is the orbit of planet 1. Planet 1. This is the orbit of planet 2. Now, we're going to do this with a two-impulse transfer. So these, again, I'm going to write this down here. These are coplanar circular orbits. Now, we're going to use a two-impulse transfer, as I said. So assume that two impulses are employed to accomplish the transfer between these orbits. So, if we're going to use two impulses, and they're going to be two impulses, the first one's going to be called delta V1d, delta V1id. This is what's going to be called the departure impulse. And the departure impulse is the one that takes us out of this first planetary orbit, delta V1, delta VD. That's what I called it, delta VID. Now it puts us onto an elliptic transfer orbit which intersects the second orbit tangentially, and then we apply a second delta V. The second delta V is going to be called delta VA, which is what's called the arrival impulse. And we will mark that with delta VAI. Now we have two impulses. Now, because we have coplanar orbits and we're doing this elliptic, we're moving on this elliptic transfer orbit. So here's the elliptic transfer orbit. We need the semi-major axis in order to be able to figure out these delta V's. So what I'm going to do is I'm going to define the semi-major axis. So we notice that A, which is the semi-major axis, I'm going to label it A on the next page here. I'm going to say let A equal the semi-major axis of the transfer orbit. Now, because the respective circular orbits have radius r1 and r2, this is going to equal r1 plus r2 all divided by 2. So we can write that down over here just for completeness. A is equal to r1 plus r2 all divided by 2. Now, we can use this information to be able to construct this interplanetary Hohmann transfer, which is that we know that delta VD, which is the magnitude of delta VD, I, that's equal to V1 plus minus V1 minus. Now, or we can actually just use it called VD plus and VD minus. Now VD minus is equal to the square root of mu s all divided by r1. I'll define all this in just a second. VD plus is equal to the square root of mu s times the square root of 2 over r1 minus 1 over a, where mu s is equal to the gravitational parameter of the Sun, because we're doing an interplanetary orbit transfer, so we're under the influence of the Sun because we're in a heliocentric phase. So now what I can do is I can compute this departure delta v, or the magnitude of this departure delta v. That's going to equal the square root of mu s times the square root of 2 over r1 minus 2 over r1 plus r2 minus the square root of mu s all divided by r1, which implies that delta Vd is equal to the square root of mu s. Now I'm going to simplify this, put it under a common denominator, and I get, when I do that, the common denominator is going to be r1 times r1 plus r2, and what's left here is I'm going to have 2 times r1 plus r2 minus 2r1, which is going to give me 2r2 minus the square root of mu s over r1. So therefore, delta Vd is going to equal the square root of mu s over r1 times the square root of 2r2 all divided by r1 plus r2 minus the square root of mu s over r1, which implies that delta Vd is equal to the square root of mu s over r1 times the square root of 2r2 all divided by r1 plus r2 minus 1. That takes care of the first impulse, and that's the one that's sitting on the diagram right here, that delta Vd that's in this diagram. So now we have the first impulse. So next we can actually work with the second impulse, which is delta Va is equal to the magnitude of delta Vai. And again, this is in an analogous way to the way we just did the first one. That's equal to V plus A minus V minus A. And now we have to figure out what these are. Well, we know that Va minus is equal to the square root of mu s times the square root of 2 over r2 minus 1 over a, because we're applying this impulse at the distance r2, which is at apoapsis of that transfer ellipse. And then Va plus is equal to the square root of mu s all divided by r2. So as a result, we wind up getting that delta Va is equal to the square root of mu s over r2 minus the square root of mu s times the square root of 2 over r2 minus 2 over r1 plus r2. And what we can do now is we can simplify this the same way we did with the first impulse. So therefore, delta Va is going to equal, well, let's look at it. We've got the square root of mu s over r2 minus the square root of mu s times the square root, and by the time we're done simplifying this, we've got r2 times r1 plus r2, but in the numerator we're going to have 2r1, and that's just because when you take 2 times r1 plus r2 minus 2r2, you get 2r1. So then that means that delta Va is equal to the square root of mu s over r2 minus the square root of mu s over r2 times the square root of 2r1 all divided by r1 plus r2, which implies that delta Va is equal to the square root of mu s over r2 times 1 minus the square root of 2r1 all divided by r1 plus r2. So those are the two impulses. So then the delta v for the interplanetary Hohmann transfer is equal to delta vd plus delta va, where these two impulses have been derived now. So as a result, we now have the total impulse. Now recall that the transfer time, so this is the last thing, is the transfer time is equal to the half period of the ellipse, right? It's an elliptic transfer orbit. So that means that the transfer time, which I'm going to define as t sub t, so t sub t is equal to pi times the square root of a cubed all divided by mu s. That's the transfer time. It's the half period of the ellipse. So we now have all the information about the Hohmann transfer. That's the interplanetary Hohmann transfer. Now, think about it this way when you're doing this interplanetary Hohmann transfer. You want to do it in such a way that when you apply that first impulse, that impulse that gets you out of that first orbit, that you're doing it as you're leaving the first planet. And then when you apply the second impulse, when you get to the apoapsis or the apohelion of the transfer orbit, then the second planet is going to be there when you apply the second impulse, so you can put yourself into that orbit and do it coincident with the other planet being there. So that leads to the question, when is it possible to perform an interplanetary Hohmann transfer? When is it possible to perform an interplanetary Hohmann transfer? Because we can't apply it, we can't just do it anytime we feel like doing it. We have to do it when the planets are aligned. So now let's draw a diagram to understand how this actually works. So again, let's put down these orbits. Now in this case, we're actually going to add to this picture the actual planets themselves, because now we need to know where the planets are when we actually apply this apply these delta v's. So our transfer ellipse is this ellipse right here. It's the same one that I already drew, and it starts at a point on the first orbit and it ends up at a point on the second orbit, such that this line that I draw here, that's the line of apsides of the transfer ellipse, where the bottom point here is the periapsis and the top point is the apoapsis of the transfer ellipse, or the transfer orbit. So if we're going to do this transfer now, we actually need the timing to be exactly as I've labeled it right here, which is that as we apply the first impulse and we get onto this transfer ellipse, this point right here has to be planet 1 at departure. Because remember, the radius here, this radius is R1, which is the radius of planet 1, and this is the radius of planet 2, of the orbit of planet 2. So this has got to be planet 1 at departure. Similarly, this right here has to be planet 2 at arrival. In other words, when the spacecraft actually gets to apoapsis, planet 2 has to be there. So now, these two planets, when we started the transfer and ended the transfer, have to be in other locations. So the first location I'm going to draw here, I'm going to put here. This location right here is the location of planet 2 at departure. So that's where planet 2 was when the transfer started. And then this last point over here, this point right there, that is planet 1 at arrival. In other words, when the spacecraft arrives at planet 2, then that's where planet 1 is when that arrival happens. Now, you can actually see that in order to be able to do this, we have to define a construct which allows us to be able to see the relative location of these planets. So the relative location of the planets is defined through a quantity called the phase angle. So we're going to define this thing called the phase angle. Now, how we define the phase angle is as follows, is that let nu1 be the true anomaly of the orbit of planet 1. And then nu2 is the true anomaly of the orbit of planet 2. Now we're going to measure the true anomaly from the line of apsides. So this line of apsides right here, that's the line from which nu is measured. So all the true anomalies are going to be measured from that line right there, because that's actually the direction from the sun to the first planet at the start at this departure point. That's actually the direction of the periapsis, the eccentricity vector of this transfer orbit, because remember, this is the transfer orbit and it's elliptic. This is an elliptic transfer orbit. Now we're going to use this information to define the phase angle. So then phi is equal to nu2 minus nu1, which is defined as the phase angle between planet 1 and planet 2. Now, given that we've done that, we can do the following, which is we can get each of these true anomalies in terms of a quantity called the mean motion. So next, we're going to say let n equal 2 pi over tau equal the mean motion. Now this is just a general term, which is the mean motion. So from this, we can actually define the mean motions of each of the planets. N1 is equal to 2 pi over tau 1 is the mean motion of planet 1. And then N2, which is 2 pi over tau 2, is the mean motion of planet 2. Now, we have to remember that tau is the orbital period. So it's the same orbital period that we have defined previously, and so tau 1 and tau 2 are the orbital periods of the orbits of planets 1 and 2, respectively. Now, what we can do is, using this information, because these orbits are circular, we can actually very easily, so because the planets move in circular orbits, we can write that nu1 is equal to nu10 plus n1 times t, and nu2 is equal to nu20 plus n2 times t, where nu10 and nu20 is the initial true anomaly of planet 1, and nu20 is the initial true anomaly of planet 2. Now, as a result of that, we can actually compute the phase angle, which is then the phase angle, which is equal to nu2 minus nu1, is equal to nu20 plus n2 times t minus nu10 plus n1 times t, which gives that phi is equal to nu20 minus nu10 plus n2 minus n1 times t. Now, given that the phase angle is defined as the difference between the true anomalies, we now know that nu20 minus nu10 is phi 0, which is the initial phase angle, plus n2 minus n1 times t, where phi 0 equals nu20 minus nu10 equals the initial phase angle. Or the phase angle at time t equals 0. So we can now look at that picture again, and we can see what that initial phase angle is. We actually see that the initial phase angle is this angle right here. So if we draw this angle, that is the initial phase angle, because that's where both the planets are at departure. And so the difference between their true anomalies is the initial phase angle. Now, what we can do is we are going to use a construct a little bit later on that will help us be able to understand how the timing actually works for being able to do this orbit transfer at the right point so that we coincide with the planets. So we're going to define a quantity which is going to be called the Synodic Period. So we're going to say let tau s be the time interval or duration over which the phase angle changes by 2 pi. Now, the 2 pi change in the phase angle basically means that the phase angle is back where it started before. So if there's a phase angle phi and we add 2 pi to it, then that's the same phase angle because angles wrap every 2 pi. Now, this could actually amount to an increase in 2 pi or a decrease in 2 pi. I just said a change in 2 pi. It could be either way, depending upon what the relative motion is between the two planets. So this quantity tau s, where the phase angle repeats, is what's called the Synodic Period. And it's when the phase angle changes by 2 pi. Now, this is where what I said earlier is that note phi can either increase or decrease with time depending upon the motion of each planet, or I should say the relative motion of the planets. Now we're going to consider the two different cases. So the increase or decrease in phi depends upon n1 and n2. So there are two cases. The two cases are n1 is greater than n2 and n1 is less than n2. So we're going to look at each of these cases now. So case 1 is n1 is greater than n2. So in this case, if n1 is greater than n2, that implies that 2 pi over tau 1 is greater than 2 pi over tau 2, which implies that tau 1 is less than tau 2. So if tau 1 is less than tau 2, it means the orbital period of planet 1 is smaller than the orbital period of planet 2. So that implies that the orbital period of planet 1 is shorter than the orbital period of planet 2. So that implies that planet 1 moves with a larger speed than planet 2. So if planet 1 is moving with a larger speed than planet 1, if planet 1 is moving with a larger speed than planet 2, that implies that the phase angle decreases with time. And that's because the phase angle is defined as nu2 minus nu1. So planet 1 is moving faster than planet 2, then that means that phase angle has to decrease. So that means that tau s is equivalent to a decrease in phi by 2 pi. So if phi 0 is the initial phase angle, what that tells me is that phi 0, if I subtract 2 pi, that's going to equal whatever the phase angle was initially, plus n2 minus n1 times the synodic period, from which I can actually solve for the synodic period. So I get that the synodic period is equal to 2 pi all divided by n1 minus n2, and that's when n1 is greater than n2. Now let's look at the other case. Second case is case 2, and that is n1 is less than n2. So let's go through this exact same argument, which is n1 is less than n2 implies that 2 pi over tau 1 is less than 2 pi over tau 2, which implies that tau 1 is greater than tau 2. And by analogy, that means that the orbital period, so now if we're going to go through this again, that implies that the orbital period, as I said, the orbital period of planet 1 is longer than the orbital period of planet 2. So that means that planet 1 moves more slowly than planet 2. So that means, we're going through this exact same setup as we did before. That means that phi increases with time, because again, phi is nu2 minus nu1. So that implies that tau s is equivalent to an increase in phi by 2 pi. And so you go through the exact same logic, which then implies that phi 0 plus 2 pi has to equal phi 0, and it's plus n2 minus n1 times tau s, which implies that tau s is equal to 2 pi all divided by n2 minus n1, and that's for the case n1 is less than n2. So now let's look at these two results. So let's look at this last result right here with this arrow, and let's look at this result right here, which I've now labeled with this arrow. You can see that in both cases, in the first case, n1 is bigger than n2, so n1 minus n2 is positive. In the second case, you see that n1 is less than n2, so n2 minus n1 is positive. So the general result for either case is that tau s has to equal 2 pi all divided by the absolute value of n2 minus n1. Now, there's another form that we can write this in, and we can also write that tau s is equal to the, so we've got 2 pi divided by these two synodic periods, and these two synodic periods are 2 pi all divided by tau 2 minus 2 pi divided by tau 1 in absolute value, which the 2 pi's cancel out, and we get 1 all divided by 1 over tau 2 minus 1 over tau 1, which is equal to tau 2 times tau 1 all divided by the absolute value of tau 2 minus tau 1. So that's an alternate expression. So that means that tau s, which is equal to 2 pi all divided by the absolute value of n2 minus n1, is also equal to tau 2 tau 1 all divided by the absolute value of tau 2 minus tau 1. So that's the synodic period. So now what we can do is we can actually figure out from the diagram what the start phase angle needs to be in order to be able to make the transfer possible. So this is how we're going to do this, is that if you go back and look at the diagram, so we're going to go back a few pages here to this diagram. So if you look at the diagram, you'll see that this was the phase angle that I marked, phi 0. Now you can see that in the amount of time, which is that transfer time that I indicated, that half period of that transfer ellipse, in that amount of time, planet 2 had to move from its initial location to this final location that I've marked. Well, that amount of angle, that angle, is n sub 2 times the transfer time, where again, the transfer time is the same transfer time that I defined earlier. That transfer time being pi times the square root of a cubed all divided by mu s. It's that same transfer time. Now, from this, you can actually see that because that's a half circle, then we know, so that phi 0 plus n sub 2 times t sub t has to equal pi, which implies that the initial phase angle has to equal pi minus n sub 2 times t sub t. So this is the initial phase angle. And you can see that we know the transfer time. Remember, the transfer time is known. I just wrote it down. So that's a perfectly known quantity. So we actually have the initial phase angle. Once we have the initial phase angle, we can actually get the final phase angle. So then we know the final phase angle is equal to the initial phase angle plus n2 minus n1 times t sub t, which implies that phi f is equal to, well, I have an expression for phi 0. It's pi minus n sub 2 times t sub t plus n sub 2 minus n sub 1 times t sub t, which implies that phi f is equal to, let's line this up, phi f is equal to pi minus n sub 1 times t sub t, and this is the final phase angle. So now let's mark that on this diagram. Go back here. There is the final phase angle right here. This angle right there is phi f. So now we have the final phase angle. So that completes the outbound interplanetary Hohmann transfer timed in such a way that we leave at the same point where planet 1 is and we arrive at the same point where planet 2 is. So it times correctly. So if we use the phase angle that we've derived, that initial phase angle, that's the phase angle that as long as the planets are in that relative alignment at the start of this interplanetary Hohmann transfer, we will arrive at the right location, and the final phase angle between the planets will be given by this value, phi sub f. So now what we can do is that once we have this configuration, we can ask the next question. And that next question is as follows. When is it possible to perform a return interplanetary Hohmann transfer? So, in order to do this, I'm going to draw this picture yet again. I'm going to clean up some things in this diagram because some of the stuff isn't necessary, and it may actually be better to have a cleaner diagram. So, here's the orbit of planet 1. Let's make this a little bit bigger. And here's the orbit of planet 2. Now we know that when we're done with this transfer, when we finished it, this is where planet 2 is on arrival, and this is where planet 1 is on arrival. So this is planet 2 at arrival, and this is planet 1 at arrival. Now, and this is the phase angle that we just computed, this final phase angle, phi sub f. So, we know that when we actually started the transfer, look at, planet 1 was actually located down here. So I'm going to mark this in red. Planet 1 was actually here at the start of the transfer. So, in order to be able to execute a return transfer, we need to traverse the same angle during the return in order for planet 1 to be back at that red location when we execute the return transfer. So here's the return transfer, right? The return transfer is also an elliptic transfer orbit that takes us from the second orbit, or the orbit of planet 2, back to the orbit of planet 1. Now, if we're going to be able to do that, then planet 2 has to be in the location at departure that in the same way that planet 1 was in the location for its departure on the outbound leg, now on the inbound leg. But where does planet 1 have to be? Well, planet 1 has to be in a location such that it's going to traverse that same angle in order to get down to where the red location is. So I'm going to mark this one in blue. That has to be this location right here. So what I'm going to do now is I'm going to describe this in a slightly different way. So this was where planet 2 was at arrival, but this also has to be where planet 2 is at departure of the return, right? So that's where planet 2 is. 2 is at departure of the return. Well, if that's the case, then this blue this is where planet 1 has to be at departure of the return. This is the return transfer. So you can see the sun is now, again, it's in the middle, that this angle right here, that angle is equal to minus phi f. So that means in order to start the return, to start a return transfer, phi has to equal minus phi f. So we're going to start everything now with this configuration. We're going to start this whole thing by developing the conditions for the return, which is that you can see that, and I'm going to mark this in green, that planet 1 was in the location that it was at arrival, and in order for you to start the return, you have to execute this after waiting this amount of time. You have to wait until this planet 1 has actually gotten into this location. So this green line is the amount that planet 1 has to have moved in order to get it into the right location, so it's where the blue is. So you have to wait a certain amount of time. So in order to start the return, we have to wait. So it's necessary to wait. So the return can only start after a waiting period, or a waiting, I want to call it a wait, after a wait time. Now, I'm going to call that wait time T sub W. Well, what is that wait time T sub W? Well, the way we're going to do it is this, is we're going to say let phi prime be the phase angle during the return. Well, we know that phi prime at t equals 0 has to equal phi f, because that's the final phase angle from, that's equal to the phase angle at the end of the outbound leg. So now we know that if that's the case, we know that phi prime has to equal phi f plus n2 minus n1 times t, which implies that phi prime at time t equals tw has to equal phi f plus n2 minus n1 times t sub w, right? But phi prime at tw has to equal minus phi f, and that's because that's what I have in this diagram right here. That's the configuration that has to be true to start the return, right? To start the return. So that implies that minus phi f has to equal phi f plus n2 minus n1 times t sub w, which implies that t sub w has to equal minus 2 phi f all divided by n2 minus n1. So this is the wait time. That's the first wait time. And it's the first wait time, as I'll get to in just a minute, because there's going to be more than one possible wait time, which I'll explain in a minute. Now, and that's because remember that the configuration repeats itself every tau sub s time units. So the phase angle changes by 2 pi every tau sub s time units. So basically that's every synodic period, right? And equals every synodic period. Now, given that that's the case, there's going to be a phase angle change every synodic period. So that means that every wait time, or all the wait times are given as that original wait time t sub w plus k times tau sub s. These are all the wait times, and I'm going to label this as twk, and this is all the wait times, the possible wait times. Now, you can see again that this is going to depend upon the values of n1 and n2. There are going to be two cases. So there are two cases, and these two cases are n1 greater than n2 and n1 less than n2. So we're going to do each of these cases separately. So we know that case 1 is n1 greater than n2. So if n1 is greater than n2, then that implies that tau sub s is equal to 2 pi all divided by n1 minus n2, which implies that t sub w plus k times tau s is equal to t sub w plus k times 2 pi all divided by n1 minus n2. But that is equal to minus 2 phi, you got to go grab this t sub w, which is minus 2 phi f all divided by n2 minus n1 plus k times 2 pi all divided by n1 minus n2, which implies t sub w plus k times tau s is equal to, now if we flip the sign on this, we get minus 2 phi f all divided by n2 minus n1 minus k times 2 pi all divided by n2 minus n1, which implies that t sub w plus k times tau s is equal to minus 2 phi f plus, let's write that f nicer, plus 2 pi k all divided by n2 minus n1. And this is for n1 greater than n2. So that is equal to t sub w k, and that's equal to minus 2 phi f plus 2 pi k all divided by n2 minus n1. Now let's look at the second case. So case 2 is n1 less than n2. So in this case we have that the synodic period is equal to, so we're going to go through this exact same argument here, which is 2 pi all divided by n2 minus n1. So if we go through the exact same logic here, we're going to wind up with t sub w plus k times tau s is equal to t sub w plus k times 2 pi all divided by n2 minus n1. And now we're going to start substituting in here, and that's going to equal, let's make this just a little bit smaller to give ourselves a little bit more space. So we've got plus k times 2 pi all divided by n2 minus n1, which is equal to minus 2 phi f all divided by n2 minus n1, and then we've got plus k times 2 pi all divided by n2 minus n1. And so now we go through this again, and we wind up with t sub w plus k times tau s is equal to, now in this case we wind up with a minus sign, and we've got 2 phi f minus 2 pi k all divided by n2 minus n1. So now we have the two possible cases, which is that this is equal to t sub w k is equal to minus 2 phi f minus 2 pi k all divided by n2 minus n1, which implies the general result. So the general result for both cases is that t sub w k is equal to, well, it's equal to the first case minus 2 phi f plus 2 pi k all divided by, let's go grab it over here so we don't guess, n2 minus n1, and this is for n1 greater than n2, and it's equal to minus 2 phi f minus 2 pi k all divided by n2 minus n1 for n1 less than n2. And if it turns out that any of these values of twk, so if twk is less than 0, then it means that this wait time, this kth wait time, is in the past. So in that case, k needs to be increased. I could say it this way. Then k needs to be increased until t sub w k is greater than 0. That is, the wait time is in the future, because you can't go backward in time. So this lecture has now taken us through these two constructs, and these two constructs are the following, which is we constructed what's called an interplanetary Hohmann transfer, and then we constructed what are called rendezvous opportunities, when let's say it this way, that provide configurations, and these configurations are defined by the phase angle, when it is possible to execute or perform either an outbound or an inbound interplanetary Hohmann transfer. The outbound takes us from planet 1 to planet 2, and the inbound brings us back from planet 2 back to planet 1.
And that is going to be the end of this lecture. In the next lecture, we're going to start looking at the constructs of leaving or departing from a first planet and arriving at a second planet, and we're going to do that through a construct called the sphere of influence, which is going to be the next thing, which will involve what's called the patched conic approximation. So we're going to end this lecture here.